Okay, so rate is always anything divided by delta t. Any parameter that we're working with, okay, and we'll do different examples, any variable divided by t as shown as a rate of change in time, okay, because when you put it over delta t, now you're asking yourself the question, okay, according to time, how much are we getting done every certain interval of time? So even if you think of velocity, okay, velocity is actually, velocity is actually, it's the change in displacement, delta represents change, okay, divided by the change in time. That's how we actually obviously get meters per second to the -1 meters per second. Okay, so in velocity is the rate of change of displacement, and acceleration, the rate of change of velocity. So in rate of reactions, okay, we have the rate of reaction, so it's reactants or products. Okay, so basically what I'm trying to say here is that if we want to calculate the rate of the reaction, we can calculate the rate at which products are changing or the rate at which reactants are changing. Okay, how fast are the products, how fast are the reactants being used up? That's one way to calculate the rate of reaction. Alternatively, how fast are the products forming? That's another way to calculate the rate of reaction. Okay, so in this particular section, there's multiple ways of measuring rate of reaction, resulting in multiple different units for rate of reaction. There's no set units for rate of reaction. I could calculate the change in concentration over time, and that would give me a particular rate of reaction. And the units would be concentrations units, moles per decimeter to the -3, divided by time. Also, it just depends what time we choose to use. We could use per second. And that results in the unit for rate of reaction being moles per decimeter to the -3 times second to the -1. That could be, you know, what am I looking for? What's the word I'm looking for? Units for rate of reaction. Okay. Rate of reaction can be measured in different ways. What happens if I use change in M, which is change in mass? Okay. So, of course, it's going to be grams divided by, let's say we want to calculate grams per minute. So we can divide it by M, okay, which is represents minutes. Okay. And then the rate of reaction would be measured in grams per minute. Okay. And that's another unit of rate of reaction potentially. Okay. I could calculate delta N, change in moles. That's 2 moles per second. Okay. And the rate of reaction could be measured in moles per second. Okay. So like how you get, what's a common example is speed. Okay. Or we call it velocity. Right. How fast are you traveling? 120 kilometers per hour. Okay. So that's a rate of change of obviously displacement. 120 kilometers is displacement per hour is the time. Okay. So let's look at the next one. Delta V, which is volume in this case, not velocity. Delta V, just another example. So this could be decimeters cubed per second as well. And we would measure the rate of reaction in that particular case as decimeters cubed per second. Okay, so this is just kind of explaining what rate is and being introduced and not scared of the concept that rate is actually measured in different ways. Okay, so for example, velocity is always in meters per second. That doesn't change. But the rate of reaction is just calculating how much something, one of the products or reactants is changing per unit time. Okay, per second, per minute, per hour, whatever it is for the particular question. All right, so we'll do examples and it will make more sense, hopefully. Let me discuss quickly the collision theory. Okay, so a little bit of theory. No pun intended. The collision theory, okay, states that particles must collide. Okay, so now we're talking about reactions. Okay, so in reactions, what happens is just say we have a bunch of reactants and we heat them up together. So they're going to start colliding. Okay, they're going to start moving. Something has to happen in order for the reaction to take place, and collision theory fits in with that, right? So particles must collide. Particles must collide with enough energy which is greater than or equal to the activation energy. Okay, and particles must collide with the correct orientation. Okay, so meaning they must bump each other at the correct angle or the correct place. Okay, so they must collide. They must collide with enough energy that is greater than or equal to the activation energy. So remember, activation energy has what definition? Activation energy is the minimum amount of energy required for the reaction to start, basically, for the reaction to take place. So what that is we have a bunch of particles inside a box. Like, for example, let's consider this, right? We have a bunch of particles inside this box, and just say they're a bunch of our reactants and they're not moving, let's say. And we heat this box up, okay? Now, once we heat this box up, the particles start moving around, okay? They gain kinetic energy and they start moving around. So they start moving around and this starts moving around all over. And eventually, they're going to collide with each other, okay? Randomly, they're going to collide with each other. Now, collision theory says they must collide, number one. Number two, they must collide with enough energy. So just say they're going very slow, boom. Maybe they won't react, but it goes fast enough, maybe then they'll react. And that amount of energy required is known as the activation energy. They must bump into each other. They must collide with the right amount of energy. Okay, so sometimes maybe we need to heat this box up even more with higher temperature to give it more energy in order for the reaction to take place, right? And they must collide with the correct orientation. So let's just say that the point of collision for this particular object needs to be here. Let's use. And the point of collision for this particular object also needs to be there. Okay. Now, in this case, if they collide like this, that's not going to work. Okay. The way they'd have to collide is maybe this here would have to be rotated. And eventually they'll collide. Okay. So that's just, this is a bit of a little diagrammatical understanding of what an effective collision is, or what they colliding with the correct orientation. Obviously, this is just an example. However, it happens in reality is different, right? Different particles need to collide with different kinds of orientations. Okay, but that's what it means. And the last two result in an effective collision. An effective collision. Okay, the collision that actually is effective and would result in a product. Okay, so particles must collide. They must collide with enough energy greater than or equal to the activation energy, and they must collide with the correct orientation. Now, let's quickly talk about the factors that influence the rate of reaction. And the first of which is temperature. Okay, and that's a little definition of temperature, or description rather of temperature, is the average kinetic energy of the particles. The average kinetic, the average kinetic energy of the particles. So what happens here, okay, this is low temperature. Perhaps the particles are moving very slowly or they're not moving at all. And once we increase the temperature, so at high temperature, these little arrows indicate that the particles start moving around. So actually, when we increase temperature, the rate of the reaction increases. Okay, so the rate of the reaction increases because we increase the likelihood we increase the likelihood of the particles colliding. And that is exactly what increases the rate of reaction. Because if I increase the likelihood that these particles are going to collide, then in a short amount of time, the reaction is going to take place. because now they're going to bump into each other more. The reaction is going to occur quickly because now they're bumping into each other more. Whereas here, in order for the reaction to take place, they need to bump, but there's low temperature, so they're not moving at all, or they're not moving much, right? So it's going to take forever for them to collide, forever for the reaction to actually occur. But now if I increase the temperature, I start moving them out more, moving, and they're going to collide more frequently, increasing the rate of reaction. Right, let's talk about concentration. So here, okay, we have a decent concentration, but as you can see, when we compare it to the one on the left, so here we'll say low concentration. And on the right, we can say this is high concentration. So I increase the concentration of one of these compounds, one of these atoms. Okay, the smaller one, I increase the concentration of that guy. Okay, but now why does a higher concentration increase the rate of reaction, which it does, by the way? So why does the higher concentration or change in concentration affect the rate of reaction? Simply because now, as you can see, because there are more particles in this given amount of space, that's what increase in concentration means, the likelihood of them colliding is more. Here, this particle had to travel all the way there to collide, or there, or there, or there. Whatever, this guy just has to go here, here, there. So it's going to start moving around. When they move around, they're going to collide more frequently, bumping into each other. So it increases the likelihood of collisions, which increases the likelihood of effective collisions. Okay, remember, not all collisions are effective, which is important. Not all collisions are effective, meaning not all collisions are, the atoms collide with sufficient kinetic energy and with correct orientation. Okay, but how do we increase effective collisions? Simply increase the amount of times they collide. Collide more and more and more and more, and eventually they will collide with enough energy and the correct orientation. But if they're colliding once every while, then what's the point? Okay, then there's obviously a slower rate of reaction. Okay, let's look at pressure, which, concentration can be described as a number of molecules per unit volume. So essentially how much you have in a given space. So pressure is force per area. Okay, so pressure is force per area. So here we have the exact same atoms and the exact same atoms. It's just that I decrease the area. I decrease the volume. I force them closer together, which increases the pressure. Now, in a smaller environment compared to a bigger environment, I hope that you can see that the chances of them colliding are way higher. Because now it just has to go boom. This has to move there, etc. Okay? Yeah, this app is not working with me today. Okay, let's just quickly change the colors or reason. Okay, either way. All right, so I hope that you can see that when we increase the pressure, it would increase the chances of collisions, which would increase the chance of effective collisions. Okay, I hope you understand. If you don't understand that concept of collisions increasing the chance of effective collisions, then let me know. Okay, and therefore we'd increase the rate of reaction. Let's look at the catalyst. Okay, so a catalyst does absolutely nothing to the atoms, does absolutely nothing to the concentration of them, does nothing to the pressure of them. What it does is something that's a bit more difficult to visualize. So a catalyst speeds up the reaction by lowering the activation energy. Remember that activation energy is the energy required to start up a reaction. So what happens essentially is a catalyst doesn't increase the amount of collisions. It increases the amount of effective collisions directly. How does it do this? By lowering the activation energy. So perhaps here, this could have bumped here with that speed and it wouldn't have reacted. But on this side, it would have bumped with the same speed and it would have reacted. Okay, so it would have bumped with the same amount of energy, but it would have reacted. So as you can see on the left-hand side, the activation energy is 250 joules. So when they collide, it needs to collide with that amount of energy. And perhaps initially, perhaps they don't collide with that energy. So there's less effective collisions. But on the right, activation energy is now 100 joules. So now, even though they collide less, they collide just as much as on the left-hand side. But now the chances that they're going to actually have an effective collision is higher because the activation energy is lower. So they collide even with that same slow speed, but it might react because now the activation energy, the energy required to start the reaction is lower. Okay, activation energy is like kind of like an entrance fee. Okay, on the left, the entrance fee 250 Rand. You'd have less people coming because of expensive. But lower your activation, lower your entrance fee to 100 Rand, more people would come. It's cheaper, right? So similar concept with this activation energy. Less effective collision. So there's still the same amount of collisions on the left and on the right, but on the left, there's less effective collisions. There are less that are actually result in the reaction occurring because the activation energy is high. It needs a lot of energy. But on the right, there's lower energy required. So perhaps the chances of there being effective collision is higher. So surface area. The smaller the particles, the larger the surface area. Okay, so the way we can think about this is, for example, this could be a tablet. I don't know how great of a diagram it is of a tablet. Okay, and this could be that same tablet, but in powder form. So in this tablet, you know, a Disprin, for example, it reacts with the water. Okay, it dissolves in the water. And what happens with the Disprin is that the outer particles react first. Of course, these particles are stuck inside. They have to wait for the outer particles to react first, then they can react. Then these particles will react. Then these particles will react. And finally, the particle in the center will react. So as you can see, that can take pretty long. Okay, that can maybe take long. Like, it may take a while for the water to reach the center of this tablet and for the water to react with these inner molecules of this tablet. Okay, so what happens when I powder that tablet? If I crush it, now just say this: you crush that powder and you decide to pour it in, you decide to put it into the water. Now every particle is dissolved in the water, so it will dissolve much quicker because now every particle is exposed to the water. So it's almost like every single particle is going to react immediately because now it's all separated. So instead of being held together where the outer particles are going to react first, then the inner layer, then the inner layer, then the inner layer, then the center eventually. Here we crush it and we drop it in and almost everything reacts instantly because now it's almost like the water is the particles are, all the particles are exposed to water at the same time. Here only the outer particles are exposed to this water or whatever liquid it may be reacting with. Okay, so this is perhaps like the solid tablet. Okay, and here we have the powdered form where it's spread open. Okay, and all can react almost at the same time. Okay, and the smaller the particles, the larger the surface area, the more spread out they are. Okay, so here we have one big tablet. Here we have that split into smaller particles. Okay, with a larger surface area. Okay, so we'll come back to this, but I just want to read through it for now. So how do we use the collision theory to explain why certain reaction has a higher rate of reaction than another? Okay, so again, we'll come back to this when we do a question, but I just want to read through it. So we have to mention the factor. So the factor is either one of these: temperature, concentration, pressure, catalyst, surface area. So we have to mention the factor. So whatever the factor is, that's different between the two reactions. So for example, temperature is different. Maybe temperature is lower in one and higher in another. We've got to mention that. Then we mention that there are more particles that have sufficient kinetic energy. Therefore, there are more effective collisions per unit time, and therefore it causes a higher rate of reaction. So these last three are like set answers that you've got to add at the end of each question. You know, if you've done any past papers, come across these questions, 4 marks, right? Use the collision theory to explain why this has a reaction A has a higher rate of reaction than reaction B. Okay, and then there's a change for temperature, which we'll discuss as well, but essentially that's what it is. Now let's quickly discuss our energy change graphs. And to see that I have everything myself. No. Now let's discuss our energy change graph. Okay, so this is a potential energy First, course of reaction graph. Now you must be asking, what is course of reaction? Course of reaction is just basically describing the fact that the course of reaction as the reaction occurs. We're not adding a time, okay? But it basically represents time without any units, without any particular unit. So course of reaction as the reaction is taking place. So it's potential energy versus course of reaction graph. Now, the particular one we're dealing with is exothermic, and I'm going to show you why it is exothermic. First things first, at the start of the reaction, we always have our reactants. So right here is where the reactants are situated. And this is actually the energy of the reactants represented here. Okay, so from here to here, this is what? This is the energy of reactants. Of course, measured on the y-axis as with the potential energy. So from 0 till where the reactants start is going to be the energy of our reactant. Where we end off is the products. That's the logical way that how a reaction takes place. All right. So that from here to here, okay, what is this? This is the energy of the products. Okay, from 0 to whatever this value is, potential energy is measured in joules. Okay, so therefore, whatever reading we get is going to be in joules. Okay, so that's the first two things. Firstly, energy of the reactants from 0, so the energy of the reactants. And we end with the energy of the products. Okay, and from 0 till that line is the energy of the products. Now, let's work our way to this guy. And this is known as the activated complex. So we start off with reactants. It takes us to the energy activated complex, and then we get products. Okay, so just one last thingy. Therefore, of course, from here to here, let's do this. Some of you may be saying that this is what? Activation energy, but it's not. This is actually the energy of the activated complex. Okay, so yeah, this activated complex, let's define it quickly. Okay, activated complex is a highly unstable, high energy transitionary state during which bonds are being broken and formed. It's a highly unstable, high energy transitionary. Transitionary meaning we are changing from reactants to products. We are transitioning from reactants to products. During which bonds are being broken, the bonds of the reactants are being broken and formed, the bonds of the products are being formed. So we go from reactants to this highly unstable state, just between reactants and products to get products. So at the activated complex, we're not like really reactants, nor are we really products. We are in that middle where we're transitioning from the reactants to the products. Okay, so now let's talk about an energy that it takes to go from here to here. To go from here to here, this Remember, we're going from the reactants to the activated complex, to this transitionary state where bonds are being broken and formed. This is known as the we know this concept, activation energy. It's the energy required for reaction to start, and I hope that you can see that it makes sense now in this graph. To go from reactant to this activated complex takes this energy. You heating up, you giving energy to these reactants, get it to the activated complex so they can turn it into products. Okay? Moreover, this is also the same and has the same value as what? Sorry. Okay, right? This is also known as the amount of energy that is absorbed. Okay, essentially absorbed. How do we understand that? Right? We've got to use up the energy that the reactants has, okay? And then we release that energy, okay, to form the products. We've got to use up the energy that the reactants already have, the potential energy that it has, and then we release that energy to form the products. So to get from reactants to the activated complex, that's the amount of energy we absorb. That's activation energy. Energy we absorb, activation energy. Okay, we can, I guess, move this a little bit. Can move this also a little bit. Okay, so very important, keep that in mind. So now we start off at energy of reactants. We boost our way up to activated complex, which is the highly unstable, high energy transitionary state during which bonds are being broken and formed, right? Thereafter, once we reach this transitional state, now it's time to start forming products. And that's where we get this guy. All the way here, okay? To get from the activated complex to the products, we need to release energy. And therefore, this here, this amount of energy is the energy released. Okay, to get from that activated complex to the products, we release energy. Okay, cool. So one more thing, I know it looks a bit messy. Okay, one more thing that we need to discuss is delta H. Now, in this case, delta H is less than 0. This is always the case for exothermic. Okay. How do we obtain that negative? Okay, simply because delta H, and we'll discuss what delta H is in a second. Ooh, that's a bit green. Delta H, okay, is calculated by taking the energy of the products and minusing it from the energy of the reactants. The energy of the products and subtracting it from the, or rather subtracting the energy of the reactants from it. I will. Okay, that's how we calculate delta H. So if we look at this particular case, we can see that the energy of the reactants is higher, is more than the energy of the products. So if I'm going to say energy of products minus energy of the reactants, I'm naturally going to end up with a negative answer, which is why delta H is definitely less than 0. Now, what is delta H? Delta H basically is called enthalpy okay, and enthalpy. And it gives us the heat. It describes to us the heat of the reaction. Is more energy released or is more energy absorbed? When more energy is released, as you can see here, more energy is released. That's a greater arrow than that. It results in an exothermic reaction. Okay. When more energy is absorbed, it will be endothermic. Okay. So delta H we calculate by calculating the difference. Delta H on this particular graph can be represented right here. Because the difference when I say energy of products minus energy of reactants, it's going to give me this value, either positive or negative. Okay, so delta H is the last thing that we put onto this graph. So same concept applies for what's this guy? This is the endothermic graph. Okay, so it's also a potential energy okay, versus course of reaction graph. Okay, and the difference between these two graphs is going to be that here the energy absorbed is this much. And the energy released is this much. So as you can see, energy absorbed is more than the energy released. That results in an endothermic reaction. This is the energy released. Okay. Furthermore, what else do we have here? Delta H is different. Why? Let's look at the products and reactants. Energy of the products is this much. Let's use this one. This is the energy of the reactant, sorry. But the energy of the products is more. So the energy of the products is more than the energy of the reactants. And in that case, it will result in a positive delta P, because I'm saying the bigger number minus the smallest number. So in this case, sorry, did I say delta P? I meant delta H. Delta H is equal to, again, it doesn't change. EP minus ER. And in this particular case, it would be greater than 0. Why? Because EP is a bigger number than ER, so it's a positive number. Okay, here we can say it would be less than 0. Okay, if there's any questions, please ask me and we can clarify it. But I hope that makes sense. It's a little bit messy, but hopefully the sense is there. Let's look at the effect of a catalyst, okay, on this particular graph. So remember we said a catalyst, it speeds up the chemical reaction by lowering the activation energy. What the catalyst does not do is increase yield of product. It does not give us more product. It does not form you more product. It does not use up less reactants. It doesn't do any of those things. It simply speeds up the rate at which your reaction occurs by lowering the activation energy. It doesn't tamper or mess with any formation of the products. It just lowers the activation energy. What a nice guy. So here we have this graph, same thing. We showed the activation energy originally, but this dotted line represents the path with a catalyst. Okay. And what happens here is, as you can see, this is the original activation energy, but with a catalyst, it follows this alternative path. Okay. And it lowers the activation energy. It's no longer that high. It's now this high. Okay. So this is an EA represents activation energy. Activation energy with a catalyst. Okay. The activation energy with the catalyst doesn't go all the way up. So it's a quicker path. It provides this alternative quicker path. So it starts here. And we don't have to go all the way up and down. We can just start here, boom, right there, and we're all the way to the product. So as you can see, the catalyst basically lowers the activation energy, but it takes you to the same products. Okay? You start off at the same place, you end off at the same place. It's just you don't need to go as high, resulting in a faster rate of reaction. Let's discuss the Maxwell-Boltzmann energy distribution. Please stop me if you have any questions. The Maxwell-Boltzmann energy distribution curve. So before we go through this nice diagram, I'll do one quickly. I'll just draw a rough one over her. So the Maxwell-Boltzmann distribution curve is a set of axes that represents on the y-axis, the number of particles, molecules. Obviously, the higher we are, the more molecules we are dealing with on the, like, obviously y-axis, right? And then again, this is the course of reaction. So as it takes place over time, no units. Now, let's extendo a little bit. Now, Maxwell-Boltzmann distribution, let's represent the most basic one. It starts off like this and then sort of goes like that, right? Okay. Then we have a little line here. Sorry, this is wrong, I believe. This should be, I don't know where I fixed it. Nowhere, it seems like. Should be energy, I'm pretty sure. Let me just yeah, should be energy. Okay, in joules, of course. So this is energy. So it's number of particles versus energy graph. And we have this line which represents the activation energy at a certain point. So let's think of this numerically, okay. The energy is at 100, and it's 200, and it's 300 until, okay, maybe it turns out 600 joules is the amount of energy required for this reaction to take place. Now, what's represented by this? Number of molecules. So the higher I am, the more molecules I have. So let's look at this point in particular. So maybe this point in particular says, okay, this has joules, 50 joules, and here it represents 25 molecules. So all this is saying is that, okay, that when we have 25 molecules, okay, that would require sort of 50 joules of energy. And the more it goes, the more it requires. So activation energy, okay, is a certain value, certain energy along this graph. So the way also you can think of it, right, is obviously the higher we go, the more molecules we have, more molecules, yeah, 50 molecules, etc. Now, what happens is these are for the reaction, okay, that everything after the activation energy. So the activation energy we represent by a line for a good reason. It's because everything after the activation energy, all the molecules here, okay, that obviously return a value to the y-axis. These are the molecules, okay? These are the particles with effective collisions. So the ones before have no effective collisions. So until the particles until we reach activation energy, essentially, so the particles increase and they decrease as we go along, whatever it is, right? Before we reach activation energy, there are no effective collisions. And then after the activation energy, all those particles represent effective collisions. Okay, kind of weird to understand, but I hope it makes sense. Now, let's see what different changes affected. So when you increase concentration, for example, when we increase concentration, what happens is, let's extend this guy a little bit. When we increase concentration, what happens is, this graph, you have more particles. So this graph goes higher. because now on the y-axis, this is 20 particles, 50, 70, 80, 600, whatever. So the graph would go higher, okay, and it would go like this. Okay, the other one is nice, something like that, for example. So because I increased concentration, it gave more particles, which resulted in more collisions. As you can see, there's more ineffective collisions even. Ineffective. There's more collisions that are not effective. But when we increase the number of collisions, we also increase the number of collisions. So now you can see that how many of these pass the activation energy, all of this, including the original one. All of that. Now there's all of that have effective collisions. Okay, so that's what happens with concentration. Steeps up the graph, more particles, more collisions, more effective collisions. Let's look at temperature. So what temperature does, okay, it flattens out the graph. Okay, flattens out the graph and ends later. Again, resulting, let's get rid of this guy. We talked about that. Resulting in more effective collisions, all these extra ones. Obviously, the pink is included in the initial. Now, all of these particles have passed the activation energy, and those are effective collisions. So that's what temperature does. Okay, increase in temperature, does that. Okay, now let's look at the catalyst. Okay, adding a catalyst simply decreases the activation energy. So it moves this line to the left, makes it lower, lower value. So now this new, let's call this is the activation energy. What? With a catalyst. So the activation energy with a catalyst is less, resulting in what? Not more collisions, more of these pass this mark. More effective collisions per unit time. All of these are now effective collisions because they collide with, these are the particles that collide with energy greater than past the activation energy. So that's what happens with a catalyst. Okay, so Maxwell-Boltzmann distribution, number of particles / molecules versus energy. Okay, and each change, increase in any of those, okay, how does it affect it? So let's look at the nice graph. Number of molecules versus course of reaction, my foot. It's number of reactions versus energy. Okay, so 1 divided K. Okay, now, yeah, so just have a look at this, right? And it's described as well. The graph goes straight up, the graph becomes flattened, and EA moves to the left. Okay, so yeah, just one thing, I just want to describe temperature quickly. So just keep in mind for all of these, right? It includes the red as well. Like for example, the yellow includes the red. The purple includes all of this region, anything that's passed. Okay, and obviously this blue would include, for when we move it to the left, all of this. Now, just for the temperature, just a quick explanation. It's the purple one in this case. It flattens it out because it doesn't have as many collisions. It has more effective collisions because we increase the speed. Okay, so when we increase the speed, they collide more frequently. Okay, but because they start colliding frequently, there's less collisions before we start having effective collisions. Okay, it takes, there's less ineffective collisions and there's more effective collisions because we increase the speed, so they boom, 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 bouncing around, they colliding more quickly. They're colliding not more, but they collide quickly and more in a shorter amount of time. Okay, so yeah, hope that makes sense. If there's any questions of anything that's still confusing about this, please let me know. So yeah, let's quickly, I know time's up, but let's quickly discuss the graph. graphs. So in this, not like any graphs in particular, but just a general overview of these graphs, right? So we have, what is this? Graphs. So we have a product graph, right? So a product graph, okay, is, as you can see, we start off with low or nothing actually, and we create product. So this is, for example, mass versus time, okay? So we start off with low mass or nothing at all. It should actually start from 0. Start from nothing and we start increasing over time. Now, quickly, what I wanted to discuss here is, as you can see, it's an increasing gradient. Okay, which means we're starting with no product and we increasing, or we rather, okay, before we discuss gradient, we start off with 0 mass, and then eventually it increases in mass. The y-axis value is increasing as time is increasing. So that means we start off with no product, we end up creating product. Then we talk about gradient. Gradient is also increasing. Now, gradient is important because the gradient, okay, if we talk mathematically, the gradient is, okay, and always in physics and chem, you can calculate gradient like this. It's the change in the y-axis. Okay, it's y, just like how it is in maths, y2 minus y1, but now we call it the change in the y-axis, whatever value is there, divided by the change in the x-axis, whatever value is there. So in this particular case, it's change in m divided by change in t. Okay, and that's the rate at which mass is changing. If you describe that, the rate at which mass is changing. And what we need to note very importantly, if you remember from the very first thing we discussed, that when we discuss the change in mass over change in time, this is the rate at which the product is being created, if that makes any sense, because it's a product graph. The rate at which this product is being created, this is what delta m divided by delta t is calculating. That gives me the rate of reaction. That gives me the rate of reaction. Okay, very important. The gradient gives rate of reaction. For these product graphs and these reactant graphs, gradient gives the rate of reaction. Okay, and if the gradient is increasing, that would result, of course, in an increasing rate of reaction, meaning the rate at which this product is being created is increasing. If the gradient is decreasing, then of course it would result in a decreasing rate of reaction. Now, just keep in mind, okay, when it comes to rate of reaction, right? Okay, let's move this down. For products, okay, let's start with reactants. For reactants, we have a positive highlight, a negative rate of reaction. But for products, we have a positive rate of reaction. Now, why is that the case? Simple understanding. Because, okay, wait. Did I lie? Yes, I lied. Let's rather just discuss this concept when we come back. It has to do with grain. It's not always reactants and products. It's to do with, it depends on the graph. Okay, we'll go through it next week either way. So that's the graphs. Okay, so this is just a general overview of graphs. It's not any particular graphs like vertical projectile motion. Ooh, these graphs are coming out. But you deal with graphs all the time. Product graphs, they'll show you, and you need to be able to read off graphs. So